Swayam Prabha. Digital India. Educated India.
Hello, welcome everyone to today's lecture on the series of modeling of multiphysics system. So far in the last 5 lectures, we have looked into the concepts of mathematics, and that was our first segment for this series of lectures. We have discussed vectors and vector fields. We have looked into how the different vector operators work, what their significance is. What is a divergence operator, what is a gradient operator. You should be by now be able to realize the physical significance. Gradient gives us the slope or the direction of the slope from low to high. Divergence gives us the net influx or outflux or the source and sink effect. Likewise, we have talked about curl. We've also seen a couple of theorems like the Gauss divergence theorem, the Stokes theorem. These have certain applications and would be useful. Then we have also gone over the concepts of non-dimensionalization or dimension analysis, what's the importance of dimensions. We have seen how changing of basis does not affect the governing equation. However, selection of the right parameters for doing the dimensional analysis is important for getting a solution. We have applied those concepts into general differential equations. We have taken without having a physical significance or value, but we have seen how that the dimensionalization would work and different types of constants that can come out from those aspects. Then in the last 2 lectures, we have gone in depth and probably quite quickly over the different methods for approaching these equations numerically, how they can be applied into a computer simulation or a computer software, how you can program the computer to evaluate the solution of an unknown variable, whether the solution is linear or non-linear, whether the system is ordinary differential equation or partial differential equation. The systems can be coupled and likewise. Right. So in all of these examples and the different practices have been undertaken so that we are at a stage where we can start with doing real life or practical problems. So from this segment, this is the second segment for the course, in which we will be looking up into the single physics based models. So I would believe anyone with an undergraduate degree in mechanical engineering has an understanding of heat transfer, maybe some degree of mass transfer, solid mechanics, fluid mechanics. You may not be very familiar with electromagnetism or electrochemistry. However, we will go over each of these physics as this coursework is a broad coursework. It is applicable for different streams, and each of you might not have been in touch or in access to some of the other physical concept. However, what you will realize in these segments is that our approach will not be an undergraduate approach. Our approach towards a problem will be on developing an understanding of how you can create a model. By model, I mean a set of governing equations and a set of boundary conditions. How those boundary conditions can be defined so that your problem set is established. Right. With this, we will start our second segment, and we will go into the thermal transport or the heat transfer segment. Okay. So heat transfer is a very well known concept. It is the transfer of energy from a body of a higher temperature to a body of a lower temperature. So, and the understanding is that heat is transferred in such a manner that it obeys the conservation of energy let's call it COE, and the direction of transfer obeys the second law of thermodynamics. Okay. So, the heat transfer process is something in which you are conserving both the first law and second law. By first law, you are conserving the internal energy and the work and heat associated with this, and by second law, you are conserving the direction of energy transfer. Okay. Modes of heat transfer, everyone is very well familiar with the modes of heat transfer. We have conduction, convection and radiation are the three modes of heat transfer. This picture over here, you can see that this log is burning and is generating heat. The heat is heating up this rod of iron, and the heat is getting converted from this hot tip to the cold end and through this metal. So, that is our conduction mode. The heat is being is heating up the fluid, that is our air nearby. That hot air is rising up and is heating our hand. This is called convection. And then on the side, the heat is getting radiated. So, this is a spelling mistake. So, it is a radiation effect. So, the heat is getting radiated from the side through electromagnetic waves, and that is a mode of radiation. So, these three modes, let us just go into some detail. So, in conduction, the heat is transferred via the oscillations of atomic lattice and / or free electrons. Okay, so this is in a very broad concept what heat conduction is. So, if you have a material with you, assume this pen, and this pen is made up of a certain crystal structure, a certain structure of atoms or some arrangement of atoms, which can be random, which can be arranged based upon whether it is crystalline or amorphous. It's composed of electrons. There might be some metallic pieces into this which has free electrons. There are some plastics which does not have the free electron. So, in that regards, these when you heat up one end, these molecules will start vibrating. They are already vibrating at room temperature, but this vibration increases as you heat it up, and you can assume that these are attached by springs. As these would be vibrating, the energy will be dissipated or transferred from the higher vibration zone to the lower vibration zone of this pen, and that is how the heat is being conducted. Likewise, in metals, since electrons are free and electrons can carry a larger portion of heat, in the case of metals, the electrons are something, assume that this is made of aluminum or copper, and the free electrons will be able to carry the energy from the hot end to the cold end. However, it is to be considered that there is no net movement of electrons, otherwise there will be an electric current. Okay. So, the energy is transported by either random oscillations or random collisions rather of electrons in a metal and lattice vibration in a non-metal. So, non-metal will include ionic species or covalent species or semiconductor devices Okay. So this mode of heat transfer, the heat flux is given by the Fourier's law. So Q vector is a heat flux vector by conduction is equals to minus K gradient of temperature. Again, this is a vector. The unit is watt per meter square. K is the thermal conductivity. Some people do also write this as K underscore in subscript TH to indicate thermal conductivity, because K can also be used for other things. For example, ionic conductivity, kappa or K is used, right. So, in this case, K is thermal conductivity. The unit for this is watt per meter Kelvin. Okay. Again, this is a vector. The direction is normal to the heat transfer plane. If you want to find out the net heat transferred, heat slash power transferred by conduction, then you multiply this with area, then you will get Q conduction or Q dot conduction, which is equals to minus Ka del T dot with the surface normal. Okay, the unit is watt. So the power transferred or the energy transferred energy is a scalar. So the power transfer, the energy transferred is you are multiplying with the area normal or integrating over the area. And for that case. Now, I've taken a minus sign over here, it is of significance. Gradients are, so let me write it down again. So Q vector due to conduction is equals to minus K del T. This is Fourier's law, or well, a modified form of Fourier's law, which will be K A del T over L or del L. Right, in which del T is T hot minus T cold, right. So, we take Q is equals to, so we take the temperature difference as Th minus Tc. It is from the higher temperature to the lower temperature, because heat is transferred from higher temperature to lower temperature, and we indicate the direction in that way. However, we know that gradient operators give us a slope from the lower value to the higher value. Right, so it will always go from the smaller value and towards the direction in which the value is increasing. So this value, this gradient of T will always be from a lower temperature to higher. To compensate for that, we add a negative sign. Okay, I think that makes the concept clear. Right. Now let's go back to our case for the metals and the conductors. So in metals, the heat transfer occurs by several electrons moving back and forth, and the atoms, among the atoms, in a disorganized or a random fashion. It is needed to be disorganized so that there is no net electric current. So you can realize that in the case of metals which has free electrons, the heating up of the metals from one end to another end, or the heat transfer from a hot end to a cold end, these free electrons would be the major energy transport carriers, right. These will be oscillating and vibrating, and these will collide with each other, and each collision would transfer the heat energy from the higher vibration zone, that is the higher temperature, to the lower vibration zone, that is the lower temperature. If you would allow the electrons to also move, or if the electrons also started moving, that will create an electric current. Electric current will not move in this case because there is no potential difference. There are a few materials which do create a potential difference. Those are thermoelectric materials in which a voltage difference is created due to a temperature difference. We were not talking about those kind of materials, but in general, the electrons collision is what is transferring heat. So there is a relation which is called the Wiedemann-Franz law, which relates the electrical conductivity with the thermal conductivity. So LT equals to K over sigma, where L is the Lorentz number, T is the temperature, K is the thermal conductivity, and sigma is the electrical conductivity. Okay, the Lorentz number value is 2.45 10 to the power of minus 8 watt ohms per Kelvin square. Okay, so this Lorentz number, it relates the thermal conductivity to the electrical conductivity at different temperature. In the case of a semiconductor, or for an ionically bonded or a covalently bonded species which does not have free electrons, the lattice vibration mode dominates. Stronger bonds between atoms, which means stiffer lattice structure, will allow better heat transport. Okay, so you can assume that these are made up by these lattice structures, and these are joined by springs, which is so these would be vibrating back and forth, and as the lattice would vibrate, the energy would be transported. The mode of energy transfer is called phonon transfer. Right, so the phonon is the equivalent particle for lattice vibration for heat transfer, just like photon is the equivalent particle for the electromagnetic radiation transfer. For the EM waves, it is photon. For the heat wave through a lattice, it's called photon. All right. The second mode of heat transfer is called convection. So the heat is transferred by a combination of conduction and advection mode. Okay, so the heat is transferred by conduction from a hot surface to the fluid, then the fluid motion advects the heat. Right. So you have a fluid in contact to a hot surface, or a hot fluid in contact to a cold surface. Both ways would work. So you have the surface on which there is a flow, or a fluid is stagnant somehow. That depends on free or natural or forced convection. This hot surface is giving the heat to the fluid. This is by conduction. So the fluid is near to the surface. The heat is getting conducted from the surface to the fluid. Then the fluid gets heated up, and if there is a flow or a motion, if it is stagnant, then due to density difference there would be a flow or a motion. That motion will then carry away the heat, and that is called advection. So it's a combination of conduction and advection, and that's why it's called convection. So we can take an example of a boundary layer. So this is a flat plate material is at a hot temperature T hot and the surrounding is at a cold temperature T cold. Our boundary layer looks like this. So say that we have two boundary layers. We can have a thermal boundary layer and we can have a momentum boundary layer. So we will talk about boundary layers later. So this is our profile. For those who know what boundary layer is and what fluid is, they would appreciate this mode. So the fluid is flowing over a plate and this is a velocity profile. So this is your u as a function of some height y. So this is a function of y. Our thermal boundary layer looks like this. So it has a higher temperature at the bottom and is at the lower temperature at the top. So there is a thermal variation through this boundary layer. Heat is getting conducted from this hot plate to the fluid, and then the motion of the fluid is carrying the heat away. This overall phenomena is called convection. Now convection heat transfer is given by the Newton's second law. In which the Q dot due to convection is equals to H times A T minus T infinity. Okay, that is our convective mode. If you want to find out the heat flux, then the heat flux Q vector due to convection equals to H T minus T infinity in the ns direction. Yeah, so there is no gradient that will give you the vectorization or the direction, but you have a cross section. Say my hand is hot and there is air and the air is flowing over my hand. This motion of air on top of my hand is convecting out. So the direction normal, that is perpendicular to this plane, will be the direction of the heat flux vector. Okay, then we have radiation. So radiation and the heat transfer occurs via electromagnetic waves from the surface to the surrounding or vice versa. Through a medium or vacuum. Okay, so through a medium or vacuum, the heat is being transferred, but there is no fluid motion, there is no heat conduction, there is no lattice vibration. It is just the formation, the transport by electromagnetic radiation. Mostly heat transfer and such are in the domain of our infrared to microwave region. Even microwave is not heat transfer. Infrared region is where most of the heat transfer occurs. So IR waves or IR radiation, infrared radiation is what is transporting the heat away. Okay, the formula for radiation, Q dot radiation. Again, let's write the units. This is watt per meter square. H was our convective coefficient. That was watt per meter square Kelvin. T is our surface temperature. So you can write Ts. So this is our surface temperature. And this is our surrounding temperature, or the free stream temperature. Q dot radiation is equals to epsilon sigma A T for the surface to the power of 4 minus T infinity to the power of 4. Okay, where epsilon is the emissivity, it is how much radiation it can emit compared to a black body. Sigma is the Stephen-Boltzmann constant. A is the surface area or the exposed surface area, and Ts and T infinity are again the surface temperature and the surrounding temperature. If you want to write this in terms of the heat flux, this one dash vector, epsilon sigma Ts to the power of 4 minus T infinity to the power of 4 in the ns direction. So again to the normal to the surface which is radiating out, it will be the direction of the heat flux. So this unit is watt, this unit is watt per meter square. The unit of the Stefan-Boltzmann constant is watt per meter 4 Kelvin. Okay. Now thermal resistance. So, so far we have considered the heat transfer by the different modes just based upon the formulation, right. Now, one thing you would need to appreciate is how these formulas come up. So, when we were talking about dimensional analysis, we have seen that formulations are developed based upon physical observation. We observe some phenomena, say this pen is dropping onto my hand, there is some forces which are attracting this pen towards my hand, that is, it is falling due to under the influence of gravity, and there is some force which would stop this pen upon collision with my hand. So, there is some physical phenomena that is happening. Based on those physical phenomena, we are developing a law or an equation that governs that physical phenomena. So, these equations, for example, conduction was found or was initially discovered by Fourier. This phenomena existed. He did some experiments. He was able to see a relation in which the heat flux was transferred was proportional to the temperature difference and was inversely proportional to the thickness of the slab, right. It became an empirical relation. It was not derived based upon exact ab initio calculations, but it was done based upon experiments. So, experiments were carried out, a line was fit against it, and on that basis that law was developed, the Fourier's law was developed. Likewise, for Newton, the Newton's law of cooling and convection is a law that was developed based upon observation. And so, all of these are based upon observation. Some physical phenomena was seen, and accordingly that formula came up. And this formula we have been using for hundreds of years now. Okay. Now, it sometimes becomes easier if to adopt another analogy which makes a complex system simpler. So, we are very much familiar with electrical resistance models in which resistors in series add up in resistance, resistors in parallel are inversely added up. These things we know very well. So, if we can relate our heat transfer to an electrical resistance, then if we have a complex body, we can very well define such bodies very quickly. Okay. So, assume that you have a slab. Okay, you have a temperature TH and you have a temperature TC. So, there is a temperature difference. You have your temperature profile looks linear as of now. We have some heat flux being transferred through this, that is say Q or Q dot, right. This you can relate to a resistance connected to a battery having a voltage V or delta V and a resistance R and a current I flowing through this. Okay. So, the electrical counterpart delta V is equals to IR. This is our Ohm's law, and we also know that Q dot is equals to some delta T into K into area over, let's just redefine this. If delta V is equals to IR, say the delta V is equivalent to delta T. So, this temperature difference is same as voltage difference, that is what is causing the energy transfer. If there is no temperature difference, there would be no energy transfer, right. So, you need a TH-TC difference. So, that is same as your voltage difference. You need a say a 5 volt battery, your negative is 0, your positive is at 5 volts. Likewise, your temperature difference, your surface may be at 30 degrees, your hot body might be at 60 degrees. So, you can have an energy transfer between them. So, voltage is equivalent to temperature difference, current is equivalent to the heat transferred, that is the net energy transfer. If that is the case, then if we write our equation, put these values over here, then delta V becomes delta T, it will be equals to the current becomes Q dot and the resistance becomes our thermal resistance. Okay, let's rewrite this equation. So we will have Q dot will be equals to delta T over R thermal. So this is of our interest, is called the thermal resistance. By different modes, we can define the thermal resistance. So for conduction, Q dot conduction equals to K A delta T over L for an L thickness body, and the cross section area is A. So if you rewrite it in terms of this, so Q dot conduction equals to delta T on L over K A. So our R thermal therefore is L over K A due to conduction. In case of convection, equals to H A delta T, which is equals to delta T over 1 by H A. So R thermal due to convection is equals to 1 over H A, and due to radiation, Q dot radiation is equals to epsilon sigma A T to the power of 4 minus T infinity to the power of 4. We can rewrite this as epsilon sigma A T square plus T infinity square T plus T infinity T minus T infinity. This is our delta T, which is equals to delta T over 1 by epsilon sigma A T square plus T infinity square T plus T infinity. So R thermal due to radiation is equals to 1 over epsilon sigma A T square plus T infinity square T plus T infinity. Okay. So we now have a set of resistances. These resistances we can then connect in series and parallel. So let's just take one quick example. Say that you have two blocks of say length L1 and say length L2 having thermal conductivity K1 and K2. The temperature difference is TH and TC. You want to solve for this problem, you can very well find the equivalent thermal resistance. This is in series. So your R1 will be equals to L1 by K1 into A. They both have the same cross section. R2 equals to L2 over K2 into A. R therefore will be equals to L1 by K1 plus L2 by K2 into 1 by A. And we can then substitute this R value back into our equation, and we can find out the relation between Q and delta T. Okay. So thermal resistance analogy are good. They are useful when you are solving for steady state problems. You know the delta T, you want to find the heat flux, or you know the heat flux, you want to find the delta T. If you want to find the intermittent temperatures, you can find out the resistances, the net heat transferred. In series, the Q will remain the same, the voltage is different. In parallel, the Q is broken down, and then remember the temperature difference remains the same. So series parallel, the same analogy as in the case of electrical would work in the case of thermal. Okay. Now these are all for steady state analysis. We are now would like to go into something that is more complex, something that is more applicable to the real life, and that is any arbitrary volume which has a changing temperature, and the heat is transferred from the system to the surrounding or back. Such a system, which is a general system, is something we are interested in. So let's assume an arbitrary volume. There's a reason I am saying this is an arbitrary volume. Just take any volume, any mass. You can take this pen, you can take my hand or my fist, you can take this watch, any arbitrary volume V, okay, which is bound by a surface del V equals to S. You have some heat transferred, say for now outside from the surface, that is your Q vector, as our surface flux, that q vector s, right. So, for this arbitrary, for an arbitrary volume, bound by a surface, the internal energy rate is q dot internal, will be an integral over the volume. So, it is mCp delta T, right. The internal energy is mCp delta T for a solid. Cp and Cv are the same for solids. So, m is rho into V. Since it is an arbitrary volume, we can take an integral over the V. So, it is rho into Cp into T into dV. Now, this is a rate and this is energy. So, this is in watts, this is in joules. So, we need to do a differential with respect to time. Okay, this is our internal energy for the given volume. Now, assume a flux. So, assume heat flux is lost from the surface, or the heat is lost from the surface as a flux. That is our q vector s, where q vector s, say if it is conduction, equals to minus k del T for conduction. So, the net energy transferred by the surface flux will be equals to integral, this is integral over volume, this is integral over the surface, qs dot ns cap ds. Okay. Now, this is since the heat is going out from the surface, we can put a negative sign in front of it, right. So, negative sign means that that heat is being lost or heat is getting out from the system. Okay. By conservation of energy, we will have q internal energy equals to q surface. Okay. So, whatever heat is being lost will be reflected in the internal energy. If the internal energy is increasing, that means heat is getting in. If the internal energy is decreasing, that means heat is getting out. So, that is why the negative sign is there, because we have shown a positive internal energy means that heat, the temperature will rise. So, heat radiating out will need to have a negative sign to counter that. Okay, so sign convention is very important. You just beware of where the sign is, what kind of sign you are using. Okay. Therefore, we will have integration of del by del T. I am just taking this del by del T inside the integration over volume, rho Cpt dV is equals to integration over surface q dot s ns ds. Okay. So, this is our equation that we hold up. We have a negative sign over here, just to be aware. We can bring this to the left. So, integration over volume del by del T of rho Cpt dV plus integration over surface, let us write del V of q vector s dotted with surface normal ds equals to 0. Now, we have one term which is a volume integral and one term which is a surface integral, and that makes it very difficult or confusing, right. We cannot combine those terms. One is a surface phenomena, one is a volume phenomena. Then how do we combine that? Well, if you remember in lecture 2, we have talked about a theorem which was called the Gauss divergence theorem. So, the Gauss divergence theorem can convert a surface integral to a volume integral. In this case, is the divergence of the vector with the volume. This is our Gauss divergence theorem. Now, we can substitute this into our governing equation. Conservation of energy equation. We get integral over volume del by del T of rho Cp temperature dV plus integral over volume, the divergence of the surface flux into dV. We can then club these two volume integrals together. Now, both are volume integrals, rho Cp T dV equals to 0. Now, if you remember that I started with an assumption that the volume is an arbitrary volume. So, let us draw the volume again. So, this is our volume V. There is two things that can happen to this integral, either that the volume is 0 or that the integration over the volume is 0. That is one thing, which means that I can have this small segment over here and this small segment over here, and say one more and one more. This can be say plus 5, this can be minus 3, it can be plus 3, and this can be minus 5, right. So, these add up to 0, that means that the net integration over this volume is 0. But if this is an arbitrary volume V, this bigger volume, then these small ones are also arbitrary volumes, say V star, right. Then this integration should also hold in the smaller components of a larger volume, right. That is not possible if you take positive negative values. So, it is not an ensemble 0. It is at each individual element this equation should be equal to 0. For that case, you can have two things, you can have two outcomes. One is that this volume V equals to 0, which is a trivial solution, and second is that this integrand is 0. This we can do, right? We can have the integrand as 0. So, del by del T of rho Cp T plus del dot Qs equals to 0. Okay. Now, let us substitute our Qs back from our heat conduction equation. Qs from conduction was equals to minus K del T. We can substitute this over here. We will have del by del T of rho Cp T plus the divergence of minus K del T equals to 0, right. And we can take this term to the right hand side, this negative term will go away. So, del by del T of rho Cp T equals to divergence of K del T. This is our heat transfer equation, that is our that is our Fourier second law, right. And this equation is a transient heat transfer, rho is the density, Cp is the specific heat, K is the thermal conductivity. K is not a scalar. For many people would consider K as a scalar. K is not a scalar. K is a second rank tensor. Okay, what a second rank tensor means is that K is anisotropic. It can have different values in different directions. Only in the case of an isotropic system. So, only for an isotropic system, K is a constant. That means it is K into I. Each diagonal element is the same. Okay. So, if that is the case, and if rho Cp are also constant, then rho Cp del T by del T equals to K del square T. This is our well known heat transfer equation. The del square is the Laplacian. Okay, and del by del. So, this is a partial differential equation. These kinds of equation are called parabolic equations or diffusion equations. Why they are called diffusion equation? Because they are dissipating or diffusing the heat out. All right. If that is comfortable with everyone, then we can move on to the case in which we have a heat generation term. So, a modification with heat generation. What we are doing is that now this arbitrary volume, it has this mCp T term, that is our internal energy change del by del T, but then you also have with this term, you also have some heat generation. Okay. So, q dot into, let us write the old terms first, is equals to integral del by del T of rho Cp T dV. Q dot surface was equals to over volume was equals to integral over surface minus Qs dot Ns ds. This term is in the unit of watt per meter cube. It is a volumetric heat generation. What is volumetric heat generation? Is that, say, your body is generating heat within. One example is, say, your electrical wire, right? You are flowing current through it, and that is generating heat as I square R. You can also have microwave heating, right? So you're putting your thing in a microwave, and the microwave is heating it up from the bulk, from the volume, right? So it is the unit for such type is watt per meter cube. Okay, so if that is the case, then Q dot gen is equals to integral over volume into dV. Okay, surface flux, the unit is watt per meter square. This unit is watt per meter cube. Okay, now let's do our conservation of energy. We will have integral over volume Q dot internal equals to Q dot surface plus Q dot generated del by del T of rho Cpt dV ds integral over volume V dV. Okay. Then again, by Gauss divergence theorem, we can convert this into a volume integral. We can take everything to the left hand side into one volumetric integral del by del T of rho Cpt plus del dot Qs minus Qgen equals to 0. Again, for an arbitrary volume with the same argument as last time. We will have this integrand as 0. So, del by del T of rho Cpt plus del dot Qs minus Qgen equals to 0. If Qs is again conduction, then we can rewrite this equation del by del T, rho Cp, if we take it out again as common, is a constant, I am sorry, is k del square T. The assumption is that rho Cp is a constant and k is isotropic and homogeneous. The body needs to be homogeneous. Okay, so this is our governing equation. Now, let's rewrite our governing equation one more time. Let's just write without the heat transfer part, without the heat generation part. So, rho Cp del T by del T is equals to k of del square T by del x square plus del square T by del y square plus del square T by del z square. I am writing this in Cartesian coordinate. We can convert this to spherical or cylindrical coordinate as well. This is a partial differential equation. How many initial condition and boundary conditions do we need? So, this is a first order derivative with respect to T. So, we need one initial condition. And we need two each boundary conditions for individual directions. Okay. So, we have x direction, y direction, z direction. So, each individual direction you would need one boundary condition. Okay, that means 6 boundary conditions in total. Okay, initial condition is just that T at all x, y, z at time t is equals to 0 is some constant. That is our initial condition, first order. Okay, boundary conditions can be of 3 types. We have talked about this in last lecture. Let's just go over in terms of heat transfer. First is Dirichlet. Dirichlet is that T, and let's just take one dimension for now, at some constant x is equals to a at all time t is a constant. So the temperature is fixed. You take a water bath and you maintain the temperature of the water bath at one end. The temperature is fixed at that end, and that is called a Dirichlet condition. Second is called a Neumann condition. Neumann condition, the flux is fixed. So minus k dt by dx dot with the surface normal at x is equals to b and time t is a constant. So you can have fixed flux. They say you have a fixed heat being transferred through a given surface. That if you know the heat flux or the heat transfer from the surface and it's a constant value, in that case it's a Neumann type boundary condition. And the third is called a Robin type boundary condition. This is a combination between Dirichlet and Neumann. If you have convective heat transfer, the convective surface, then minus k dt by dx, well rather del t by del x, because these are all partial derivatives, dot with surface at x is equals to c at time t is equals to h times t at x is equals to c comma t minus t infinity. If it is radiative, then it is equals to minus k del t by del x dot with surface normal x is equals to d comma t is equals to epsilon sigma t at x is equals to d comma t to the power of 4 minus t infinity to the power of 4. This is for radiative surface. Okay. So, if the surface is convective, that means there is some air or some fluid that is able to convect the heat out. In this case, you can see that the flux is equals to the temperature itself, that is a Robin type. If the surface is radiative, then you can have t to the power of 4 dependence. Okay, these are just some coordinate variation. The only thing that's going to vary is our Laplacian. If the body is Cartesian, that is it's a cuboidal structure, then we can take this Laplacian. If it is a cylinder, that means that there is one axis of symmetry, and then there is a so it's rotated around one axis and then it is elongated around the other. In that case, we can take cylindrical. If it is a sphere or is spherical, it doesn't have to be a sphere, it can also be an ellipsoid. So in that case, we will take the spherical type condition. You just change those if there is some degrees of symmetry. For example, if it is radial symmetry, then your theta and z terms will be gone, or theta and phi terms will be gone, only the radial terms will remain. Okay. Say for example, for a sphere, we will have rho Cp del t by del t is equals to k 1 by r square del by del r square del t by del r. Okay. So, that is radially symmetric for a sphere. Now, we are trying to approach an analytical problem, that is this 1D heat diffusion, the transient 1D heat diffusion. I will not go over the steady state ones in this class. You have done this at undergraduate level. You can solve an ordinary differential equation. If not, please refer to Incropper or DeWitt. That book has an excellent set of examples and theory for heat transfer. We are doing this for a transient case, right? In this case, let's take a body of length thickness L, in which we have an initial temperature, say theta naught. So initially it is at theta naught, and then both sides is at 0 temperature. So theta is equals to 0 for both sides. Theta is our temperature, right? For just assume that theta is temperature. That is the reason I am taking theta not T. I will come to that. Okay. So for a 1D body, our equation becomes rho Cp del theta by del t equals to k del square theta by del x square. You take this to the right, k over rho Cp is alpha. So 1 by alpha del by del t is equals to del square theta by del x square. What is alpha? Alpha is a thermal diffusivity. That is equals to k over rho Cp. Okay. So this is our equation. We need one initial condition. So theta at x comma 0 is equals to theta 0, and this is our initial condition, and we need two boundary conditions, and that is theta at 0 and L and at all time t is equals to 0. Okay, that is our boundary condition. So, we would like to set this problem up. So, the method that we are using is called separation of variables. So, in separation of variables, we take the theta, which is a function of x and t, and we split it into two functions. One is capital X, which is just a function of x, and capital T, which is just a function of t. If you substitute this theta into our governing equation, then you will see that it is 1 by alpha. Del theta by del t, x is not, and if you do partial, x will come out, and you will have dt by dt. And you will have del square theta by del x square will only be differentiated with respect to x, and the t will come out. So, t d square x by dx square. You can make some substitutions, and you can take t to the left and x to the right. You will have 1 by alpha t dt by dt is equals to 1 by x d square x by dx square. This we can take. So, see that the left hand side is just ODE with respect to t, right? The right hand side is just an ODE with respect to x. If a t ODE is equals to an x ODE, that means that it should be equals to a constant. This constant we are taking it as minus lambda square. The reason why we took this as minus, we will come when we solve this. So, for now let us leave this problem up to this stage. In the next lecture we will pick it up from this point, and we will see why this lambda is there, how we can substitute different values, and then we will go into our lumped body analysis, some other approaches for infinite domains, and then some numerical approaches. With that we will finish, try to finish heat transfer by next lecture. So, thank you so much for listening.